Let's look at James Joules' device for determining the mechanical equivalency of heat in a little more detail. We can see that it's actually quite a simple device, consisting of a set of paddles inside a container, an insulated container of water, some hanging masses that are designed to spin the paddles inside the water, and a thermometer to record any changes in temperature as a result of this motion. Now, if you remember from our definition of temperature, we say that temperature is a measure of the average kinetic energy of all the molecules inside a substance. So if I've got this container of water here, and on average it has a certain temperature, if I set into motion these paddles, I'm going to have more collisions with the molecules, and I'm going to impart more kinetic energy to the molecules. So if our temperature is related to kinetic energy, it should go up. Now, how can I make it go up? Well, all I have to recall is our conservation of energy laws. Energy cannot be created or destroyed, but it can be transferred from one form into another. Now, initially we've got some hanging masses. They've got stored potential energy, and they're going to fall through a distance h. So in the diagram depicted, they're actually already in motion and they're halfway to the bottom. Let's start them where they're supposed to be, and I'll just quickly draw in the masses at the start of the picture. So I've got my two hanging masses, each of mass m, starting at a height h, and each of these masses currently possess potential energy before they fall. So we're starting with potential energy at the top, and I've got two of them. I've got one on this side and one on this side. Now the masses are both the same and the heights are both the same, but just for sake of clarity, we're going to label them EP2 and EP1. That's the energy I start with. And as those objects start to fall to the ground, they're going to start to gain kinetic energy. Now, from what we've learned in previous units, we know that by the time they reach the bottom, they will have transferred their potential energy into kinetic. So we're going to label that EK1 and EK2. Very easy to measure. Nowadays, we could use a simple photo gate, or back in the day, they could simply just time it. Now, in the absence of our fluid and of our paddles moving in the fluid, that should be a perfect transfer. When we're assuming there's no friction in the pulleys or anything like that. So our equation will just simply be potential energy gets converted to kinetic as follows. Now, we know that it's actually moving a set of paddles inside a fluid. And from experience, we know that that's going to actually slow down the motion. So we would assume that our final kinetic energy, EK1 and EK2, will not in fact add up to EP1 and EP2. It'll be slightly less. But we know that energy must be conserved. So that missing energy must have gone into the water. The moving paddles have changed the kinetic energy of the water. Well, how do we measure that? Well, we know that kinetic energy is related to temperature, so all we've got to do is figure out how much thermal energy the water has gained. So our equation still illustrates conservation of energy, except now we're ending with not only kinetic, but thermal energy or heat energy at the end when the water actually increases its temperature. Now it's just a matter of plugging in our variables. We know that potential energy is just mgh, so what does it look like when all is said and done? So I've got my two potential energies, M1, G1, H1, and similarly for mass 2. And those two are going to get transferred, those two potential energies will get transferred into kinetic and thermal energy. Our kinetic energy is as follows, 1/2 M1 V1 squared and 1/2 M2 V2 squared. And the thermal energy written in blue here is the energy gained by the water increasing its temperature. So we can use this formula to actually figure out the final temperature rise of the water and predict this. Let's try the question with some actual numbers. Let's assume our original masses are both 1/2 kilogram. So each of these is 0.5 kilograms. And they're going to both fall through a distance h, and let's make that distance 2 meters. Let's also assume that at the end their final velocities reach a speed of 5 meters per second for both of them. Furthermore, let's say that we have half a kilogram of water. And the question is, what is the change in temperature of the water? How much does its temperature go up? Well, let's give it a try. Let's move our page up a bit so we have some room and plug in some numbers. Now before we start plugging in numbers, let's do a little bit of simplification first. Both sides have the same mass and will each fall a distance h. So we actually have 2 mgh for our total initial potential energy. And similarly on the right, they each will gain the same final speed and both have the same mass. So at the end, we'll have 2 times 1/2 mv squared plus our thermal energy of the water. Now that makes it much easier to solve. So let's get rid of a few things. We have some room and plug in some numbers. The left-hand side becomes 19.6 joules, while the right-hand side becomes 12.5 joules for our kinetic energy component, plus our mc delta t. So our thermal energy, which we denote as Q, is going to end up becoming 19.6 minus 12.5 joules. So we get 7.1 joules is equal to mc delta t. Now we should plug in our values for the water. The water's mass was 0.5 kilograms. The specific heat of water, if you look it up in a table, is 4,186 joules per kilogram Kelvin. And we're trying to figure out its change in temperature. We only get a small temperature increase of 0.0034 Kelvin.